Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at linear combinations of vectors. So a linear combination is just something times the first vector plus something times the second vector. Here u and v are vectors, a and b are scalars. So one such example, if I have these two u and v as my vectors, a linear combination could be 2u plus v. Of course, there are infinitely many other possible linear combinations. And when we're doing linear combinations, it's actually helpful to write the vectors in matrix form. It just makes it so much easier. So I can write u like this, 3 minus 2, 1. I, then j, then k. So it's 2 times that vector plus v, which I'm going to write as 1, 1, 1. So the resulting vector is just 2 times 3 plus 1, 7. 2 times negative 2 plus 1. 2 times 1 plus 1, which is 3. So this vector is said to be a linear combination of u and v. So when we do linear combinations, we often refer to R3 or R2. R2 is the set of all points in 2 dimensions, so it's just the Cartesian plane as you've always known it, and R3 is like that extended plane we had with the x, y, and z axis. R3 contains all points in 3D like 1, -5, 0, or 0, 1, 2, whatever. So R3 is just the set of all such points. So in this space, this set of all 3-dimensional points, if you take 2 vectors and examine the set of all possible linear combinations thereof, one of 2 things will happen. Either the 2 vectors are not parallel as they were up here, in which case the set of all possible linear combinations of them forms a plane through the origin. The other possible case is that the 2 vectors are parallel, in which case the set of all possible linear combinations is a line through the origin. All right, let's look at some examples. So we are going to determine if this point lies in the plane spanned by these 2 vectors. So when we say the plane spanned, we mean the set of all possible linear combinations. So really, what I'm saying when I ask if this lies in the plane generated by these 2 vectors, I'm saying, can the position vector associated with this point be written as a linear combination of these 2 vectors? So another way of saying that, I'm asking, are there any solutions to A times u plus B times the vector V to give me the position vector associated with this point 0, -2, 7. So when I say solutions, I mean pairs of values A and B that make this a true statement. So let's replace u with this vector and v with this vector. So sometimes it's possible to find such values A and B, sometimes it's not. We just go through and solve the resulting simultaneous equations and see if the solution is consistent. So multiplying the first vector by A, I just get 3a, 4a, and multiplying the second vector by B, I just get this. So I have to see if this sum here is possible. So we need the first component to be equal, so that means 3a plus 2b equals 0. We need the second component to be equal, and then we need the third component to be equal. Now what happens when you have this situation in which we have 3 equations yet only 2 variables? We're going to solve the first 2 and make sure that that solution is consistent with the third equation. So the first 2 are pretty easy to solve because a is -2. So if I substitute that into the first equation, I get -6 plus 2b equals 0. And that means that b is equal to +3. Now we're going to check if a is -2, b equals 3 satisfies this equation. So 4 times a plus 5 times b equals 7, that's a true statement. So this system is consistent. The solution is a equals -2, b equals 3. I have just proved that this vector here can indeed be written as a linear combination of u and v. So the answer to the question, does that point lie on the plane? The answer is yes. If we had an inconsistent system, we would have no solution. The answer here would be no. All right, let's look at another example. So here we have a plane and its Cartesian equation. Now note, if I substitute x, y, and z for 0, I get a true statement. This is a plane that passes through the origin. So what that means is I will be able to find two non-parallel vectors that generate this plane. In other words, this plane will be the span of two non-zero and non-parallel vectors. So how do I go about this? Let's take our Cartesian equation and rearrange it to make one of the variables the subject. It's easiest to make z the subject since it has a coefficient of 1. So writing z by itself, I would get z equals -4x plus 2y. That's actually very helpful for us. It means that any point that lies in such a plane has the form x coordinate, y coordinate, and the z coordinate is -4 times the x coordinate plus 2 times the y coordinate. So if we write this here as a vector, x, y, and -4x plus 2y, we can sort of split this up into components. We can write this as x multiplied, so I need to multiply by x to get the first term, no x in the second, and x is being multiplied by -4 in the third, and similarly for y, it will be 0, 1, 2. So hopefully you're starting to see that this looks awfully like a linear combination, which it is. We have the linear combination of two non-zero and non-parallel vectors. Accordingly, these two vectors can be chosen to generate our desired plane. Now note that this solution is not unique. Infinitely many other solutions exist, but we only needed one. So what we found is that on a plane with this equation, every vector that lies in that plane can be written as the linear combination of these two, that is, as something times this vector plus something times this vector. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.